In this chapter, we will be using calculus as a tool in curve sketching. In this lesson, we will be using the second derivative test.
All right, hi everybody. So now I'm going to walk you through the second derivative test. Okay. Now you may or may not want to use this. This is totally your call. This is just an alternate method for finding maximum and minimum points of a function. Let me put it to you this way. Essentially what we're doing here is we're kind of embellishing your knowledge of derivatives here, okay? So you've seen enough over the last, what I would suspect would be a couple of chapters worth of material, that what I'm about to do here should make sense, but you may not have seen the connection that I'm going to make here right now. So again, a couple chapters ago we were taking a look at finding maxima and minima of functions here. Now we're going to do the same thing. We're going to look at points where the graph changes direction, so those minimums, maximums there. And here's how we do it. At least here's another way of doing it. If the first derivative of a function at c is equal to 0, okay? If that's true, then we know that the function has leveled out, that the tangent is horizontal, and that may or may not correspond to a maximum or minimum value. Now that it might be, for example, that you've got a situation where you've got a cubic going on here and it goes flat right there. But if that's true, and at the same time the second derivative is positive, okay, which we saw in a previous lesson, implies that the function is concave up, okay, or concave, then the function must have a local minimum at x equals c, because here's what's going on here. So we know that at this value here, the slope of the derivative, or the slope of the tangent line, is going to be 0, okay, but we also know that the graph is concave up here at the same time. Well, that's what it must look like, which means that this must have a minimum value right there. Now, likewise, if the first derivative is equal to 0, and again, what we just said there, meaning that the tangent line is horizontal, and the second derivative is less than 0, this time meaning that the graph is convex, right? It's going down like this, then we can conclude that the function must have a maximum, a local maximum at x equals to c, okay? A local or relative max, depending on what your instructor is telling you should say there. And that's what it would look like. Now there's always one other scenario here that you have to consider. Well, what if the first derivative is equal to 0 and the second derivative is equal to 0? Well, then you've got that inflection point, and that actually is the scenario that I was just referring to up here. First derivative is 0 and the second derivative is 0. So it's an inflection point because the second derivative is equal to 0, and remember, and the concavity is changing. That is important. Okay, that is important that the concavity be changing here. The fact that the first derivative goes to 0 simply means that at that point the function has got a horizontal tangent. So it's really kind of a dramatic point where it changes here. It's like basically it's almost like this is where the vertex would have been if this was to continue to curve down or to continue to curve up, and that's the point that we're changing at. Okay, now there could be other inflection points as well, but that's what we're looking at that particular point here. Now, notice that this test doesn't apply if the derivative does not exist. Okay, if the derivative doesn't exist, then you've got either like an asymptote there, okay, or it could be, it could be a point of discontinuity there. It could also be the fact that the curve has gone vertical, okay, in which case the second derivative won't exist there as well. Okay, so in that chain between function, derivative, second derivative, third derivative, and so on, as soon as you get one point there where the function or the derivative doesn't exist, everything after that will also cease to exist. And so that's why this is an issue here. Anyway, it's just another way of looking at that. So let's take a look at some examples. So here we go. So this question tells us to use the second derivative test to find the local maximum and minimum points of, and we give you two functions here. So let's take a look. Let's just dive in. So first of all, number 1. Now, what we're going to do first of all, is find the critical numbers of the function, okay? And I'm saying it that way on purpose because I want to make sure we understand kind of the vocabulary here. So to find the critical numbers, what we're going to do is we're going to take the derivative. So it'll be negative 6x squared plus 6x, okay? And remember, we are interested in where the first derivative is either 0 or is undefined. Now, because this is just a nice little polynomial, it's not going to be undefined anywhere. So we're going to set this equal to 0. Okay, and then to determine where it's equal to 0, we're just going to factor that. So that will be, I like taking out the negative with that. So negative 6x is going to leave us with x minus 1. And so we've got two places here where the first derivative is going to go to 0. Okay, so we're going to have critical numbers at x equal to 0 and positive 1. So now what we need to do is figure out, well, okay, good. Now that's an indication to me where the derivative has a 0 slope, sorry, where the function has a 0 slope. Now what we want to do is we want to investigate the second derivative at those critical numbers. Now, the second derivative, when we do that, we are going to get negative 12x plus 6. Okay, so let's take and let's evaluate, let's see what's going on at 0 here. So there's my second derivative. Now let's see what it does at 0. Now, I've watched a lot of students get confused at this point here. Notice I'm not setting the second derivative equal to 0. I'm evaluating it at 0. Okay, I'm trying to figure out what the concavity is when the slope is horizontal here. Now when you plug that in, we're going to get negative 12 multiplied by 0 plus 6, which is simply going to be 6. Okay, so now what that tells me is that the graph is going to be concave up. Okay, I'll do my little smiley face there. Concave up when x is equal to 0, which suggests a local min. Sorry about that. If we take and evaluate the second derivative at 1, again, I'm not setting it equal to 1, I'm evaluating it at 1, so it'll be negative 12 multiplied by 1 plus 6, that's going to get me negative 6. That is going to be concave down, which suggests a local max. Okay? And if I go through and plug those numbers in there, okay, if I go back to the original function, and remember, I use the original function gives me the y coordinates. The first derivative gives me slopes. The second derivative tells me about the concavity or the curvature. If I want to know what those minimum and maximum values are, I have to go back to the original function. And if I plug a 0 into the original function, I get a 1. This is my minimum value. If I plug the 1 in there, into the original function, what do I get there? I'm going to get, I'm going to get 2 there. That's going to be my max value. Okay, and there we go. So that's what's going on with that first function. Now let's take a look at the second one. Okay, now, got to go back just so you remember what that is. It was negative 6x squared, okay, plus 6x plus 2. Now, in this case right here, you already should have a sense of what this is looking like. Okay, this shouldn't strike you as too weird here. That's actually one of the reasons why this is here. We already know that this is a parabola. We know that this opens down. So I'm going to make a prediction right now that when I get my my critical number, when I plug it into the second derivative, I suspect that my second derivative is going to be negative, okay, to tell me that it's going to be concave down or convex if you want to think of it that way, when I plug in that value. So let's just take a look and verify that. So my first derivative, okay, of that function that I was just showing you there was going to be negative 12, equals negative 12x plus 6. Okay, and here is where I will set this equal to 0 because I am looking for the critical numbers. I'm going to bring the 12x over, equals 6, divide, and I'm going to get x is equal to a half. Yeah, which isn't ideal. I'd rather it was a nice integer, but so be it, whatever. Now I'm going to take my second derivative, And my second derivative here is negative 12. Just negative 12. Now, because my second derivative is negative, I know that this function is concave down. But because it's not a function of x anymore, okay, it's just a constant, that tells me that it's always concave down. And that actually makes sense because it's a parabola. The curvature you'd expect would be the same all the way through the function there. It's always going to be concave down. So that tells me, therefore, that at x equals 1/2, okay, that I have got a local max. Always concave down. And actually, I can do a little bit better than that because I do know something about what a quadratic looks like. So I can tell you that this is the only place that this occurs. So I can actually do a little bit better. This is actually an absolute max. Now, if I want to figure out what that value is, I would plug that in, 1/2. I would go back up to my original function. So that would be negative 6 times 1/2 squared plus 6 times 1/2 plus 2. Half of 6 is 3 plus 2 is 5. That's going to be a half squared, so it's going to be 1/4. So negative 6 over 1/4 is going to be negative 3 over 2. So it's going to be, what is that? What did I just say? That was going to be 5 minus 1.5, so it's going to be basically negative 3.5. That's right, not negative. Sorry, I glanced right there and I drew a negative down there, just 3.5. So 3.5 is our max value for that particular function. Okay, one more question here. Determine the maximum and or minimum values of y equals x to the fourth minus 6x cubed. Okay, so the first thing we were going to want to do here, just like before, is we're going to want to take that first derivative there. Okay, and actually that should make sense. Okay, you should always be taking a derivative. In a course like this, that's like your go-to thing to do here. So x to the fourth minus 6x cubed is going to be 4x cubed minus 18x squared. Now, we're looking for critical numbers. It's a polynomial, so we're not going to have an issue where it's undefined. So we're just going to set it equal to 0. I will take out what's common, and it looks to me it's going to be 2x squared will be common, which will leave me with a 2x minus 9. Okay, and that tells me I'm going to get critical numbers where x is equal to 0 or 9/2. Okay, now I want to investigate this a little further. This is an x to the fourth. This is a quartic. Okay, so I'm just going to take a quick look here. I've got 0 and 9/2. When I think about what my function looks like, my derivative is a cubic. The 0 has a multiplicity, sorry is the word I'm looking for, multiplicity of 2. The 9/2 has a multiplicity of 1. It's a positive cubic, so it's going up. So my derivative function is going to look something like this and like that, meaning it's negative here, positive here. Okay, so I can tell by looking at this, okay, I can tell by looking at this that this is the function is decreasing here, and increasing here. Now, that means I can tell that this is probably going to be a min, but I'm going to use my second derivative test just to illustrate how that works. Okay, and I also want to look a little bit closer at what's going on here because look what I've got. I've got a decreasing and then a decreasing. What's happening there? Maybe we can get a little bit more information. So, and actually just to reiterate, maybe I'm just going to walk over to the side here. So I know that my first derivative, okay, my first derivative is less than 0 on the interval negative infinity to 0, union 0 to 9/2. Okay, it's less than 0 from negative infinity to 0, and then from 0 to 9/2, which means this function is decreasing on the interval negative infinity up to 9/2, and I'm going to include the 9/2 on that. Now, if if that's a confusing jump, I've gone through that in videos earlier than this when we were looking through the chapter on extreme values, the maximum and minimum values here. I know there were other people that have kind of a different view on this, but it seems pretty split. And I know that there's this is again a commonly held way of interpreting that. So likewise, I know that the first derivative is positive on the interval 9/2 out to infinity, which means the function is increasing on the interval 9/2 out to infinity. And I include the 9/2 here in both of those intervals. It's the end point of a decreasing interval and the beginning point of an increasing interval, and that suggests to me that that's a min. The work that I'm now going to do over here with the second derivative should confirm that. Now, my second derivative, looking back up to here, is going to be 12x squared. Okay. What do I got here? Minus 18x squared, so this is going to be minus 36x. Now, bear in mind what I'm trying to accomplish here. I'm not looking for intervals of concavity right now. What I'm looking to do is to investigate the concavity specifically at those values. So if I take my second derivative and I'm going to evaluate it at 0, that'll be 12, 0 squared minus 36 times 0. I'm getting 0 as a result. Well, now that suggests to me that I'm looking at a possible point of inflection. And I'm going to want to investigate that just a little bit because remember, a point of inflection occurs when the concavity changes. Now let's just see what's going on at the 9/2. Okay, if I take the second derivative, evaluate it at 9/2. Okay, well, actually, I'm just going to plug that into my calculator really quickly here because I want to get a decimal value for this. So just so that I have a number here that's nice to work with. Yeah, okay, that's going to be 81. And that is greater than 0, so this means that this thing is going to be concave up at that point, which suggests, therefore, a local min at x equals, I should say, at x equals 9/2. And again, I already knew that. I already had a clue there. Now, let's just go back up a little bit here and let's investigate what's happening at around 0 here. So I've got 0 here, 9/2. I just want to take a look at the concavity here. This is a parabola. My second derivative is a parabola that opens up. Okay. And my parabola that opens up here, if I factor out, if I simplify that, I'm going to get, what have I got here? I'm going to get 12x x minus 3. So I'm going to get a 0 at 0 and at positive 3. Now remember, 9/2 is 4/5. So my parabola is going to look like this. This is my second derivative. Okay, it's positive here, negative here, positive here. So notice that it did in fact change concavity on both sides of 0. That's really what I was interested in. The rest of this was not of concern to me. This was what was concerned. So I know that that point is actually a point of inflection. And actually what that suggests to me is we can go one step further here. I know that this is a quartic. I have a general idea of what it looks like. I know that it's going to go through the origin. I can see that. I now know that that's a point of inflection. So it's going to come down. It's going to level. Whoops. Shoot. You know, all I had to do was hit the x-axis coming in flat, and I didn't. So I'm going to start at the x-axis. I'm going to do what I should have done. I'm going to start here and go up like this, and go down like that. Okay? Then I'm going to come down, and when I get to 4.5, 9/2. Wow, that was terrible. 9/2, I know that that's going to correspond to a minimum. So isn't it beautiful how all of this works together? I can get basically the same information if I investigate the intervals, or if I just plug in that information, the critical numbers from the first derivative, the critical numbers, I should say, of the original function, into the second derivative, and I still can get the same image here. It's just absolutely amazing how beautifully this works together.